heat transfer part. Okay, so I just then go to my study one. You see that all of them are tick marked over here, and then I click on compute. Okay, so now if you do like this, what you will see that only the electric potential plot is coming, because we have first computed the electric currents and then added the heat transfer. So if you want the temperature plot to also come, so just right click on solver configuration, delete configuration, and delete all the configuration, right? Just write yes, and then you just go to the study one again and compute. In this case, you will just not see the electric potential, but also the rise in temperature. Okay, so you see the electric potential plot and the temperature plot also. Okay, now the question is to evaluate the average temperature, volume average temperature of the insulated domain. Okay, so how do I do that? I just need to right click on the derived values, go to average and volume average. Okay, on the volume average, I just need to add the outer domains like this. Okay, and just click on evaluate. Okay, so this session is also getting recorded, so if you have missed any points, we'll be sharing this recorded one-on-one session, I think so. So you can go through the steps if you have missed any of the steps. Okay, so this is how you evaluate the volume average. The next point is the volume maximum temperature in the cable core. To do that, I again right click on the derived values. I have maximum, volume maximum, and over here I select the inner domain. Okay, and again I just by default that expression is temperature, that's good enough, and I click on evaluate. Okay, so I have the volume average and volume maximum. Okay, not much variation. So I just then go to my file, save as, and what I do is I just save it as in my drive. Test assignment. Okay, so I saved this model file. Now I go to my app over here, and then I just browse, click on browse, and browse again, and then select the model file that you have just saved for the assignment. Okay, so it will take some time for the model to upload. Okay, and then just click on OK, and then just click on check. Okay, so if you check it now, so then if it is coming correct, then it will give you answer like congrats, you have passed the test. Okay, so just a quick raise of hands, how many people were able to get this green symbol for you guys once you clicked on check? Were you able to get any of the response like this? Yeah, so I see that some of you guys were able to get this solution done. Yeah, so if you're getting the results and unable to upload, you can just share your model files at support@comsol.com. So we'll look into that model. There's one more question, as in we didn't mesh this current geometry. We did mesh, actually. It actually happens automatically. So in COMSOL, you don't need to worry about the mesh. So if you don't select this particular meshing type, you get it as a normal mesh. Okay, so it automatically mesh your geometry. Okay, you don't need to worry about the mesh part. So there are a lot of questions. We'll try to answer as many as possible. Okay. Now, one of the question is, how can you assign air domain around the conductors? So in that case, you just need to make a block over here. So you can just make a block over here, for example, having the dimension of uh, 1 by 1 by 1. Let us just try to see. Yeah, so we'll see once you click on build all, you will see how this block looks like. Okay, so just try to make shift it towards minus y direction, like minus 0.5. Okay, and downwards by minus 0.5. Okay, that's good. And then I want to extend it to 10 meters because my dimension of my coil is 10. Okay, so just try it. So always it's trial and error. Just try to know how to do this set. So now I have made the block, which is an extra block now. Okay, like this. And then here you can assign it as air material. Just right click on the materials and just click on add material from library, and you can go to built-in and add. Okay, so here once you add the air domain, just click on this domain. Okay, so now you can see that the inner material is the copper, then you have the nylon, and then you have the air domain. Okay, so now you can also see, you can apply some flow to this air, and you can see the convection of flow, or how this, because of the flow of the air, if the cable is getting cooled down or not. You can do such kind of analysis, but to do that you need to use heat transfer in solids and fluids, not just heat transfer in solids. Yeah, there's one more question as to how to assign the parameter. So to assign the parameter is, for example, I want to make my current, which is now 2.5 amperes. I want to make it as a parameter driven. For example, I want to change this 2.5 to I naught. I want the current to be given as I naught, and this I naught is defined in the parameter. Okay, so what I do, I just write the definition of I naught over here, and in the parameters one, I use I naught as 2.5 amperes. Okay, the units are always written in square brackets. So this is how you can parameterize your model. Yeah, there's one more question that why did we shift from study 1 to study 2 and name both of them separately in the last assignment? So that is not required, to be honest. This is not required, but when you're trying to do a multi-physics analysis, it's always important to go step by step. Okay, and why is that required? Because you know need so you need to troubleshoot which interface is giving an issue or a concern. Okay, in that case, if you solve both of them together in a single study, you will not be able to understand which is a model which will give you the correct result, or which is the interface which is giving you the issue. Okay, if you do it step by step in two step, so now you have two buttons to click: study one, compute, which will do the electrical analysis; study two, which is doing electrothermal analysis. Okay, and if you click on compute in the study one and you get the results, it is converging, you're getting good results. But now if you do the study 2 and then you are not able to get the converged result, what does it suggest? It suggests that there is some issue or concern with the heat transfer module or the heat transfer interface, and that is why it's always good to do step by step. Study 1 for a single physics, study 2 for the second physics in addition. So we have one question as to how to model anode and cathode in COMSOL. So it's very much similar to how you apply the terminal ground condition. So where you apply the terminal, you give electric potential and voltage over here and give it a very high potential. And the other part, you can give it as ground, or you can give one more terminal with the negative potential. So this is how you can, using the electric current interface, you can be able to model anode and cathode. Yeah, there's one more question as to how to design pressure sensors. We have many examples of pressure sensors. One of the example is capacitive pressure sensor. So if you go to the file application library over here and just search for capacitive pressure sensor, okay, it's also available in the application library online. So you just search for over here. If you do a quick search, you will get this capacitive pressure sensor. Okay, and I will just share this link to all of you guys, so people who are interested in modeling pressure sensors can go through this. Okay, And over here, if you just open this model, okay, you can see that how to apply the pressure. Okay, so in this case, there is a boundary condition known as boundary load, where you can either give the force or you can give the pressure. Okay, so you can use that to give the load. So if you see in this case the solid mechanics, okay, and here there's the option of boundary load. So this is actually a switch kind of a device, right, where we apply this pressure on the top. We use the boundary load 1 over here, and over here you can see the pressure is given P naught, which is defined somewhere in the parameters 20 kilopascal. Okay, you can also give it a force per unit area or total force. That depends upon your requirement. Yeah, so there's one more question: how to convert 2D geometry, 2D model into 3D. You can convert this 2D geometry into 3D using one of the options. There are many options. One of them is extrusion that we did yesterday. Okay, there's another option as rotation or revolution. Also, you can do to convert it into the azimuthal direction. So there are multiple ways, and in the geometry section tomorrow, you will get to know more about how to convert 2D geometry into 3D. There's one more question on how to submit the model for a cluster. So for cluster computation, you just need to right click on the study one, and there is an option as cluster computing. Okay, and there are many blogs written specifically of how to do this cluster computing. Okay, so what I will do, I will just search for the cluster computing COMSOL blog, and I will share that with you. Okay, so this will give you fair information on how to run the model in cluster computation with the COMSOL desktop environment, and how to do that is written in detailed in this particular example. Okay, so let me just share this with you, this one and the second one, which is a knowledge based entry. So there are a lot of blogs which you might be interested to go through. Yeah, so if you're interested in solar physics applications, so there are again many different applications of solar physics. For example, you might be interested in modeling solar cells. In that case, if you're interested to model semiconductor physics, then the semiconductor model would be required. Other examples would be like you want to just know how the rays are propagating and how they are getting reflected to a certain area of domain which is of interest. If you're trying to model the rays, in that case you require the ray optics module. Okay, or you're trying to have layer by layer structure of dielectric material, and you want to try to understand how the ray propagation happens through this layer structure, then you require the ray optics module. So it depends upon what applications of solar applications that you are looking for. That particular example model would be required. If you have, for example, solar panels, and you want to try to see what are the stress being developed on the solar panels because of the flow of the air, right? If there's any buckling of the solar panels, some kind of deformation, what are the stress is being developed within the solar panels because of external winds. So in that case, you will require FSI, that is a fluid structure interaction. Okay, in that case, you might need structural mechanics module. Okay, so there are different modules required for different applications. So if I'm unable to still answer the question, please write to support@comsol.com with your specific application, and then we'll get back to you which specific modules are required for this your particular application. Okay. There's a question on how to link COMSOL with MATLAB. Are there any hands-on examples? Yes, there are some of the examples. So I will suggest you to go through this blog, COMSOL MATLAB blog. Okay, so this model is this also has the live link to MATLAB. So you can see there are some of the blogs that you might be interested, and this is the blog that I'm talking about. In this case, they are specifically shown you how to do this coupling with MATLAB. Okay, so I'll share this blog with you guys, and over here also, I think if you go to the file application library, and over here if you go to this live link to MATLAB, there are some tutorial models. Okay, in each of this model file, they have coupled with the MATLAB. Okay, so you can go through these examples also. Open its PDF documentation, for example. So there's one more question on trying to explain the heat flux boundary condition in yesterday's assignment. Yeah, so heat flux concept is also a little bit complex. It's not that straightforward. So what I will suggest you, I will also share this blog with you. This will help you to comprehend the heat transfer coefficient values for different conditions. Do I have it? Yeah, so these are the two blogs. I'll suggest you to go through these particular blogs, and they talk about a lot of the heat transfer coefficient, what are the basics of heat transfer coefficient, and what values do we need to assign for different specific cases. Okay, so I'll suggest you to go through this. You can also have the tutorial modules which are assigned in the end of these particular blogs. This is a question for labeling to MATLAB. Do we require MATLAB to be installed? Yes, you would need the MATLAB to be installed in this case. There's one more question, as in why do we delete the configuration? Why do we use the delete configuration? So sometimes what happens is that if you see over here, in the solver configuration, just right click on solver configuration and delete configuration. So sometimes what happens is that there's some cache memory, and because of that your results are not getting updated. In that case, it's always better to just right click on solver configuration, delete configuration. Okay, delete all nodes over here. Okay, and with that it will go with the if you've already done some modification of the solver settings, that also gets written off, and you can again start with the default solver if you just click on compute. Yeah, there's one more question as to model high frequency resonator using piezoelectric material. Yeah, so we have an example with the piezoelectric as well as the resonator model, that is somewhere. If I just search over here, piezo. Yeah, so we have an example of a tunable cavity using piezo actuator. So let's share to all of you guys. If you are interested, you can also go through this example. Okay, we specifically use piezoelectric materials in the cavities, which are working as a resonator. So you can see the change or the shift in the resonating frequency as and when there is a deformation of the piezoelectric materials. There's one more question: can we model plasma study in COMSOL? Yes, there are many examples. So I'll suggest you to go to this file application library and then go to this plasma over here, somewhere over here. Yeah, plasma modules. You can just go through. There are many different types of plasma modeling that you can do in COMSOL. So I will suggest you to go through these examples. You can also go through this documentation to learn more about them. There is one more question: can we model solar cells in COMSOL? Yes, you can model solar cell. So if you go to this semiconductor module and photonic devices and circuits, you will see this silicon solar cell model. Okay, so this one specifically models solar cell in one dimension. You can extend this model to be a model in two dimension also. Okay, so in this, if you just search for solar cell in the application library, you will still be able to get the solar cell models. Okay, there are many different kinds of solar cells, different applications of solar cells. So what I will recommend is you can go through all these examples. We also have, so I'm just sharing it with you, and there's also one model with the ray optics part. So you've coupled the ray optics with the silicon solar cell. This one more question: will the diffraction grating be covered as an example? No, very specific physics models will not be covered in the this training course. This training course is basically for a very specific application or a very specific role of teaching the attendees about how to do multiphysics analysis, how to make geometry, assign the materials, and the physics, have different studies, how to change or tune the solver settings, how to do the meshing, and finally post process. So we are not going to work explicitly on very specific problems, but in one-on-one session we can guide you to those examples. Like if you're interested in diffraction grating, just go in this application library and just search for diffraction. Okay, and you can see that there are a lot of examples with the diffraction, and one of them, you can do it with ray optics as well as RF module or wave optics. Okay, so that depends upon your application. For example, in the ray optics, you don't model so you model the radiation as point particles. Okay, in the RF and wave optics, you model the electromagnetic waves as the waves itself. There's one more question: how to model streamer discharge? A streamer discharge is a very specific problem. I think we should be able to do it with the plasma model. So I think if we have some example models also. Yeah, so we have an example of some of the examples. This is an example of negative streamer in nitrogen, and this is done in plasma module. There's one more example which is done using the I think this is done with the particle tracing module, or yeah, okay, it's still done with the plasma module. So I suggest you to go through some of these examples over here. Okay, so I'll share this with all of you guys if you're interested in modeling streamers, or you can also model discharges in a very quick period of time. You can go through these models. There's one more question as to can we change the particle size distribution modeling in COMSOL? Yes, you can do that. One of the example is the particles which are modeled the RBC and white blood cells which are modeled as particles. So this is example of dielectric separation. Okay, in this case, the platelets and RBC are modeled as particles with different dimensions. Okay, so you can go through this, and they are trying to move across based upon an external flow of fluid and under the difference of potential applied to the electrodes, the anodes and cathodes, which are operated at a particular frequency. So you can go through this example model. This is an excellent example model which couples the flow, particles, and electric fields. Uh, yeah. So there's one more question: can we model photonic crystal-based sensors? Yes, you can should be able to model photonic-based crystals. So just again, you just try to search for photonic crystal, and you will see that there are many examples which are based upon photonic crystals. Okay, we also have an example of photonic crystal fiber over here, and also a blog written on that aspect. Okay, so on different aspects of modeling photonic crystals, and you can see over here how we can tune this to work as a particular sensors. For example, if you have a fiber and you have holes in the fiber and you pass a particular liquid or gas through this fiber, how this refractive index are going to change, and if there are going to be any change in the modes of propagation through this photonic crystal fiber. Okay, so this is what you can actually go through this. I will just share the blog and some of the models which are based on photonic crystals, which you can go through. Yeah, there's one more question that for the heat flux condition, why haven't we selected all the components of the insulator and only the outer parts? Yeah, so that's a very good question over here. So let me just see over here, what do we ask? In the assignment, we asked for the power cable is getting convective cooled with the heat transfer coefficient 10. Yes, so in that case you can give it on the this sides, on the sideways of the copper, on the insulators also, not only the top side but also on the sides of the nylon. Okay, but I'm not sure if that is going to change or affect the results much, because the surface area of the sides over here are more dominating in evacuating the heat as compared to this dimension, which are very, very small. There's one more question that can the ray optics be used to model the laser? Laser itself is a very complex phenomena, and to model different applications of lasers, we have a blog written. So what I will suggest you to go through this blog, laser material interaction. Okay, so there are different approaches how you can model the laser with the material. One of them could be as a heat source on the surface. So you apply a Gaussian distribution of heat source on a slab which is opaque. Okay, and that particular surface, part of surface gets heated up. One more approach is indeed to use optics, that is ray optics. And we also have one example for that, how the laser is passing through the set of lens which are having a particular angle or conical angle. Okay, and because of the very high power of the laser, how it is deforming the lenses. Okay, and in this case the requirement for this kind of approach is that the systems that we are trying to model, the opticals of the lens, are geometrically transparent to the lasers. So this is what is an assumption that we have to make. Okay, so the lasers which is passing through this are like transparent. If you want to model opaque things, then you cannot model it with the optics, right? If you want to model mirrors, then you can use specific boundary conditions like a wall boundary condition along with the reflection. That is possible. Then you can also have a Beard-Lambert law. We also have that approach where you can model semi-translucent models, semi-translucent domains, and then finally beam envelope method model, that is for modeling a full wave Maxwellian approach for a very long distance through this nonlinear crystal material. Okay, so I will share this blog with you. So there are different approaches. I will suggest you to go through this approach and then see which one supports your particular application. Yeah, one more example is on modeling biosensors. Yes, definitely you can model the biosensors. One of the examples could be just search in the blog if there are any blogs for biosensors. Yes, there are many examples of modeling the biosensors based upon the applications. Okay, so MEMS device, chemical device, or graphene device. There are a lot of different applications. So I will suggest you to go through this link and see any of the blogs might be of interest to you, or any of the models could also be of interest to you. There's one more question on how to model heat transfer and phase transformation in SMA and eternal wires using due to Joule heating. So there are some of the examples of phase transformation. So if you go to this application library over here, and if you go to the heat transfer, I think over here, yeah, phase change is available over here. Okay, so if you just open the phase change, there are some of the examples which are for phase change. Okay, so I'll suggest you to go through these examples, and if it still doesn't help you for a particular example, then please write to support@comsol.com. The next question that we have is, do we have any optimization problem? Can we do any optimization model? Yes, we can do optimization. There are a lot of models. So if you go again in the application library, if you go to this optimization module, should be somewhere over here. Yeah. So here you can see that there are a lot of different examples of doing the optimization. Okay. So you have design optimization, you have parameter estimation, you have shape optimization. Okay, and then finally topology optimization. So in most of the problem, it is dealing with the definition of the objective function, and we try to minimize that objective function by varying the control parameters. Okay, so we have both gradient free and gradient based optimization. One more question is, can we model solenoid valves and its applications? Yes, you can model solenoid valves. We also have the examples over here. Okay, let me just search. Yeah, so this is a specific example of electromagnetic plunger. So you can see over here, we have the armature, contact, springs, and coil, and the yoke. And this is specifically modeled in this case. So you can see this is the multi-turn coil, and this works as solenoid. And if I see the animation, yeah, so you can see the animation that as the we apply the current in the coil over here, which is surrounding this inner ferrite material, it pulls it above. And once we put the current to be like zero, okay, this shift you can see over here, then it brings it to the initial position over here. So there's also an example model with this. So it's just to go through this particular example model along with the blog. Yeah, so there's one more question as to the difference in modeling 3D and 2D geometries. So what do we do in that case? So if you talk about modeling in 3D, okay, so if you have a structure like a cable like this, okay, so either you can go for the 3D model like this, okay, alternately, if you want to model, you can do the 2D model like a circle. So it would be actually the cross section of the copper wire. Okay, so you take this cross section like a plane to cut this cylindrical wire, and you try to model this as a circle. The difference now is that in 3D you have the end effects, that is in the starting and the end. Okay, so that is the actual model in 3D. Okay, but in 2D it is an infinite structure in out of the plane directions, that is it's from plus infinity to minus infinity. Okay, so that is an approximation that you make in 2D structures, that you assume that your structure is infinite in out of plane direction. So that is an assumption that you do when you do it in 2D. Having said that, there are a lot of advantages of doing 2D modeling. Okay, if you can take such kind of advantages, for example, the number of mesh elements reduces drastically, and it also helps you to compute very quickly with an approximately good results. But again, yes, that is an approximation. The next question is, can we model metamaterials? Yes, we can model the metamaterials. There are a lot of examples that you might be interested to go through them. One of the example, I think it should be a part of the blog even. Yeah, so there is in acoustics, this is an example in acoustics and also with poroelastic material. And if you're looking for optics, over there also there is an example in metamaterial. So if you just search over here, okay, there are a lot of examples which deals with the metamaterial. So I will I'll just share this link with you. Okay, you can just go through this example models to model metamaterials. There's one more question on how to see identify parametric results. So basically, what I can do is I use a file open and assignment solution, and in that assignment, what I do is one of the way is to use the parameter over here. So let me just yeah. So you can see over here, if I use my current as I naught, okay, and this I naught I'm giving the parameter section 2.5. What I can do is I can just instead of study 1, I can write it as parametric sweep. Okay, so I write a parameter over here. I change my current from 1 to or I can just write a range like 1 comma 2 comma 5, okay, units of ampere. So we start with 1, then it has a difference of 2, step of 2, that is 3, and then again finally ending at 5. Okay, so this is square units of amperes. This is how you define a parameter sweep. Once you compute it, now you have the evaluation at 3 different current inputs. Okay, and now if you want to evaluate the volume average of the insulator as a function of the current given over here. So how do I do that? So there are two ways of doing that. One of them is to use the derived values in the bottom, and the second way is to evaluate using the non-local coupling in the definition. Okay, so to the save time, what I can do is I just right click again on derived values. I can go for volume average. Okay, and I select all the outer boundaries, and just click on evaluate. Now you can see for 3 different temperatures, I have 3 different values of average temperature, and I can click on plot table graph, and you can see how the temperature is changing with the rise in rise in the current. I can also use line markers to see how the data points which are used at each intervals. So this is how you can do the parametric sweep and evaluate the results using the parametric sweeps. There is also a question on modeling composite materials. Composite materials, we have a specific new module that we have introduced to model composite materials. Okay, so you can go through that particular module to learn how to model composite modules. Okay, so for example, if you go to file application library, again you will see this composite module. So it will be somewhere in the top. Yeah, composite material module. So you can just go through some of the examples on those aspects. So you have some of the examples that you might be interested to model in regards to composite modeling. There's one more question of how to get the GIF from the COMSOL file. So this is how you can use the animation. I think this is available in the COMSOL Learning Center. If it is not available, we're anyways going to cover in the day 5 of the training session. So I can just show you in the day 5 how to evaluate or get the GIF animations from your results. Okay. Also, I will suggest you, I will recommend strongly that you go through the videos in the COMSOL Learning Center so that if you come tomorrow, you are prepared with this, and this will help you to get ahead with the instructors and get the results very quickly. Okay, I will share this again with you guys. Okay, so please go through this COMSOL Learning Center videos. This is freely available, and it will definitely help you to get the most out of this course. There's one more question on modeling Gaussian pulse. Yeah, so there are many examples to model Gaussian pulse. One of the example is Drude-Lorentz model. Okay, so in this example model, we have a temporal, spatio-temporal Gaussian pulse, which is propagating through dispersive material. Okay, there are some of the examples that you might be interested to go through, right? So, and then we just you can just write Gaussian pulse. Do we have any specific examples in this case? No. So I will suggest you to go through this example. This example has the Gaussian spatio-temporal Gaussian pulse to be input in the starting of the domain. So you can go through this, and there are of course the other examples. Okay, that you also would like to go through this. Okay. In short, we have this Gaussian pulse over here somewhere. So if you just right click on the definition and in the functions, and you can see the Gaussian pulse over here. Okay, so you can define the Gaussian pulse directly over here by defining what is the location of the peak of the pulse as well as the standard deviation. What is it of your pulse? Okay. Yeah, so the question on what are the unique features of COMSOL. So in COMSOL, as you can see, yeah, and you will also see in the later examples, the multiphysics applications, specifically in the multiphysics applications, so that coupling of different physics is seamless. So you can couple from one physics to another physics in a same interface or same GUI interface seamlessly, and that is the major advantages of COMSOL as compared to the other softwares. There's one more question on lithium-ion battery. We have an example on lithium-ion battery. So if you want, you can just go through that. Okay, there are many examples on lithium-ion batteries. So I will suggest you to go through these example models. Okay, and this again has the step-by-step process to make the whole model. Okay, so if you see this, download the PDF. Okay, it has the step-by-step process to make the whole model. So this talks about the theory part, and okay, in this case it might not be having because this is an app. Okay, but if you see this 2D lithium ion battery download application files, so if you just log into comsol.com, over here you'll be also able to download the .mph file. Okay, so this talks about the theory part, the results, and then the step-by-step process to make the whole model. So I would suggest you to go through these models and make the model from scratch to gain your understanding. This question of how to export file of a 3D JPEG file from the COMSOL. So if you want to export the results, for example, we have the result of the temperature profile, as you can see from here. Okay, so this is the temperature profile. Now you want to export into a .jpeg file. So you can just use this image snapshot, as you can see over here, and you can just change it to the JPEG format or any of the format. Okay, and just click on OK. Okay, and it will save it to the file where you want to save it. The snapshot, image snapshot, is available here. Yeah, Anushka. So I'm trying to share this session to you. Can you please let us know if you would be sharing the recorded version, and by when will you be sharing the recorded version, as many people were asking about the same of this one-on-one session.
Okay. Okay. Thanks. Thanks, Uttam. So I'll be sharing the recording of the session after this particular session.